柳峰さん、聞こえますか？柳峰さん、聞こえますか？
はい、今、
あ、神谷です。発表中、発表者の今カメラが映ってるやつを、一般オーディエンスの人に、なんかスポットライトで見せることってできますか？
はい、ちょっと今、深谷先生にやってもらいます。
あ、今
ありがとうございます。
なってます。ありがとうございます。
はい、よろしくお願いします。ありがとうございます。
this is one of the most important events Hokkaido University Department Symposium. So, chairperson will be done by Hokkaido University. So,
thank you very much. And I'm quite sure I'm not the right person to chair the Professor Lee's lecture, but I'm very pleased to be one of the audience, because here we'll talk about a general idea of the scientist. And I know that the many Hokkaido University people and also high school student is on the web to listen to his lecture. So he will talk universal idea of scientists. So let me talk a little bit about, briefly introduce his CV in English. He was born in city of Frankfurt in Germany, and he graduated Free University of Berlin in 1993. And then he moved to University of Frankfurt, where he was born. And then he got a PhD under the mentor. The mentor was Dr. Musra, right? Okay. And then he moved to Scripps Research Center in San Diego, in United States, California. He stayed. He told me that he stayed there 6 years in California. Maybe he enjoyed the nice weather and environment in California. And then he moved back to Germany, and he worked in the Max Planck Institute, Kohl Institute. And now he is a manager director of the Max Planck Kohl Institute. And he has lots of awards already. Let me briefly introduce one of them. 2006, he got the award, JSPS Fellowship Award of Japan. And 2009, it's wonderful, Thomson Reuters Citation Laureate, 2009. And it must be a chemical award, 2013, Mukaiyama Award, 2013. And then it's a step to the Nobel laureate, 2014, Thomson Reuters Highly Cited Researchers. It's one of the great steps to the Nobel laureate. And then, as you may know, 2021, he got the Nobel Prize in Chemistry. He's a very nice guy, and I have enjoyed his talk before, and I have learned a lot about the general science, and I expect a wonderful lecture today. And also, he is a great fan of football. You know, he's from Frankfurt, as you may know, Bundesliga, and I forget the name of the team. Eintracht Frankfurt. The name of the football team is not good well this year, but maybe the player Kamada used to play in the Eintracht Frankfurt, but he moved to Serie A in Italy. He was so depressed. Anyway, let's please start your lecture, please. Thank you.
All right, thank you so much, Professor Hawking. When I was maybe 12 years old or so, I wanted to understand our world. You know, what is the planet made of? What is matter made of? What are we humans made of? And where is the journey going? Where are we coming from? So I had these strong philosophical questions on my mind. And I guess you can formulate the question like the question of life, the universe, and everything. That was what kind of was on my mind at the time. I still had hair, and And I thought, like, somehow I didn't have chemistry at the time in school, but somehow I thought the world is made of molecules and atoms, and so are we. And the scientists that understand molecules and atoms and how they interact are chemists. So chemistry will give me the answer. That was my thought at the time. So before I even had chemistry in high school, I started setting up my own laboratory. This is a house where a friend of mine lived. And we built a laboratory down there. We had a Bunsen burner. We had concentrated sulfuric acid, potassium nitrate, coal, and sulfur. I don't know, the experts already can guess what kind of things we had in mind. And experiments was then what we did. And we got completely lost and fascinated with experiments. And one day, I had just prepared a mixture of potassium nitrate, coal, and sulfur. It's a kind of explosive mixture for those who don't know. And unfortunately, by accident, a burning match fell into this flask that I had, and 100 grams of that mixture erupted. It was not an explosion, it was kind of like a strong fire, and a lot of smoke was formed. And we had to open up the windows. And at that moment, this pharmacist that used to have his pharmacy here and who sold us the chemicals, I don't know why he sold dangerous chemicals to little kids. I mean, I was 11 or 12 years old. He realized that it was not washing powder that we were making there, but something else, actually gunpowder. So yeah, that was the beginning and quick end of my first chemistry career. And while I realized I will not find the answers that I was looking for, you know, the nature of life, the universe, and everything. I would now say what I was interested in was the understanding of the nature of reality. You know, what is reality made of? That was kind of what I had on mind. Now I understand sort of this question, but at the time I was a bit confused. I realized I will not find the answer to this in chemistry. Okay, so I can do great experiments, but no, the answer is not there. It was already too late. And I was completely hooked. And from that day on, chemistry was on my mind. And at the time, there was no internet, of course. So I rented books in the local library and read everything I could find out about chemistry. And, you know, I got a high school education in chemistry. And while I realized I will not find the answer to these things, I learned about really, really beautiful phenomena in the universe. And one of the most beautiful phenomenon in my experience, in my opinion, maybe the most beautiful and most useful chemical reaction in the solar system, I would suggest, is photosynthesis. In photosynthesis, which is happening in the leaves of plants, this is from a moss, and within these leaves, there are these little chloroplasts, and there's this green colored compound. It's the reaction center of photosynthesis. And in these chloroplasts, a chemical reaction takes place that as I said, is unmatched by any other chemical reaction in terms of beauty, because two abundant and cheap molecules, carbon dioxide from the air, you know, there's 200 parts per million or so right now, unfortunately, of carbon dioxide, and water react to give, on the one hand, carbohydrates, sugars, you know, molecules like this, glucose. This is the stuff we need to eat, right? And as a byproduct, oxygen. I think this is a chemical reaction everybody should know, must know. It's common knowledge, and you must know about this because it's like the most useful reaction for us, because this chemical reaction creates the food we eat, or the animals that some of us eat, and oxygen, the gas we need to breathe, right? Two of the most useful molecules for our life on Earth. And it's mediated by sunlight. That's the beauty. But that's not it, right? It's not enough to have carbon dioxide, water, and sunlight. You need another ingredient, a magic ingredient, and that's the enzymes that I put here. And enzymes are protein molecules. They are made in our bodies and in plants and in animals and in insects and so on. They're made out of amino acids, small organic molecules. And these amino acids assemble into long chains to form proteins, and some of these proteins are magic in that they can mediate chemical reactions. They can sort of encourage a chemical reaction to occur. And the principle behind that magic actually is catalysis. And I like to say catalysis is a single molecule away from magic, right? It's almost magic, because a catalyst can convince two molecules, let's say CO2 and water, to create something new, let's say a carbohydrate. And in doing so, it does so by reducing the activation barrier, so the process becomes chemically, sort of energetically more easy. In doing so, without being used up in the process, it can repeat the job again and again, millions and trillions and gazillions or whatnot of illions of times, right? In principle, one molecule of a catalyst is enough to create, in theory, an infinite amount of a useful molecule, for example, carbohydrates or oxygen, or any other molecule that chemists want to make, or biologists, or life in this case. So that's what really attracts me to catalysis like nothing else. And to be honest, I don't understand how you can research something else than catalysis. I think it's the coolest and most fascinating topic the universe has to offer for us. But that's only one aspect of it. The other aspect which makes it even more attractive to work in catalysis is that because of this phenomenon of turnover, that one molecule creates, a sheer infinite amount of something else, the other aspect is it's also a technology, right? It's not only the basis of our life, and photosynthesis and any process in our body is mediated by catalysts, enzymes, but it's also a key technology. And I would argue people have overlooked the relevance of catalysis. Catalysis may well be the single most important technology available for our life on this planet. And there is, to my knowledge, no other technology that contributes to this amazing amount of the global domestic product. 1/3, roughly 34 trillion US dollars, 10 to the 12. Huge amount of revenue that is generated with the help of catalysts. So I like to say catalysts feed, heal, warm, and transport humanity and their goods. And it is also clear, they have contributed to the climate change, indirectly. It's also clear that for the future problems of humanity, we will need catalysts. We will need new catalysts that solve these big problems that are coming upon us right now. And I'd like to share with you a few examples now of technological catalytic processes that I would argue sort of are fundamental parts of our culture. They are as important as the music of Beethoven or, the art of Picasso. Everybody should know about this. You should know these chemical reactions I'm sharing with you today, 4 or so. That's not a huge amount of number, and they're very simple. Reaction number 1, it's actually already number 2, photosynthesis is number 1. Number 1, and this is number 2 now, is the Haber-Bosch process. People have said it's called bread from air. You made bread out of air. How is that possible? Well, you can take nitrogen, which is the main constituent of air, and in the presence of hydrogen gas and a catalyst, an iron-based catalyst, you can unite these two elements to form ammonia. And this is done on a 150 million ton scale currently every year. It requires 2% of all energy on the planet. It's a huge amount of energy. And we need this so badly because ammonia and also its oxidation process product HNO3, nitric acid, constitute the basis of all fertilizers. So we need the fertilizers to have crops. And people have estimated that without this huge amount of ammonia that is produced every year, 150 million tons, there wouldn't be 8 billion people on the planet, as you can directly correlate the growth of the world population with the synthesis of ammonia. It's really amazing. People said maybe where there would be like 2 or maximally 4 billion people on the planet without ammonia from Haber-Bosch. It's pretty amazing. And several kilograms of our body mass are based on nitrogen that has been converted to ammonia and then into plants and into animals that we eat ultimately. So it's kind of a really, probably the single most important chemical process done on the earth for our life at least. That's reaction number 2. Reaction number 3, how to make fuel. How do we make gasoline? And a very old-fashioned way is shown here. It's called the Fischer-Tropsch process. Okay, this one you don't have to recall. It will become more important, but right now you can quickly forget about it. But at least it was very, very important at the time. 100 years ago in Germany, we didn't have good access to oil. So we had to synthesize gasoline. And the way we made it was we took coal, which was abundantly available in Germany, especially in the area where my institute is. It's in Mülheim an der Ruhr. This is the Ruhr area. You could actually dig in the grass and you would find coal in the old days. So there was plenty of coal, but no oil. And if you take coal and react it with water at very high temperature, you form a mixture of carbon monoxide and hydrogen gas. And this mixture is called synthesis gas. And synthesis gas, in the presence of heterogeneous catalysts, can be converted into alkanes, long-chain hydrocarbon molecules like this one here. This is octane. And as a byproduct, water is formed. And this, of course, can then be used to drive cars or tanks. Germany wanted to drive lots of tanks at the time, unfortunately. And it's kind of a nice way, actually, to synthesize fuel if you have no crude oil. And by the way, just so you know, Sasol in South Africa is still utilizing this, and they did so a lot during the apartheid years. And currently, actually, the biggest plant on the planet is still doing Fischer-Tropsch. It's called Pearl GTL, gas to liquid. It's in Qatar. And they make 50 million barrels of synthetic fuels per year. So it's still a big process because in Qatar, they have a lot of natural gas. And the natural gas can also be converted into synthesis gas. And then you can make Fischer-Tropsch and create fuel this way. But of course, there is an even more important process to make fuel. And that is utilizing utilizing oil as a starting material. And that is catalytic cracking, a really fascinating chemical reaction for the organic chemists here. Even for us, actually, a fascinating process because you start out with these simple hydrocarbons from crude oil, long chain hydrocarbons that you can obtain by just distilling oil. And then you treat them with a catalyst, a zeolite catalyst. This is aluminum silicate at 500 degrees. This is a very strong acid, by the way. So I'm already guiding you a little bit. And magically then, zeolite cleaves these long chain alkanes actually at all sorts of positions to sort of make lots of fragments, ultimately also molecules of this size. And these are useful now as fuel materials. So you can put this now into your car or your tank and then drive with it. And this is probably the largest scale chemical operation on the planet. Up to 1 billion ton of fuel has been made using this process. Of course, I mean, like you, I hope, this will end soon because we don't want to produce carbon dioxide by burning this material. I mean, this is a severe problem. And I'm a great fan of electric vehicles. Nonetheless, it's undeniable that this kind of operation, this catalytic operation, has ensured the lifestyle we are living right now on this planet. Okay, so this was reaction number 3. Reaction number 4, how do we make plastic? And plastic is everywhere. So again, it's not the greatest reputation, but it's a material we need for everything. And for the doctors, even like in hip replacement, you need plastic, right? And for new knee joints and so on. And plastic is made with catalysts, once again, on a 200 million ton scale. It's a huge operation. And these catalysts were also discovered in Mülheim an der Ruhr at my institute from Karl Ziegler. He was my predecessor at the institute, discovered this process in 1953, and 10 years later he was the first Nobel Prize winner at our institute. And what happens is in this process, you take propylene that comes from the cracking I've shown you before. And when you subject that to a mixture of 2 different metal catalysts, titanium tetrachloride and triethyl aluminum, you obtain the polymer, polypropylene. And polypropylene is actually a wonderful material. I mean, just don't dump it in the ocean, I would say. But you can make, buckets, you can make luggage and ropes, and also beautiful chairs, 1970 design. And, you know, if you think about it, at this point, there is no real problem with plastic. Plastic was, you know, it was just crude oil. Then you crack it, you then polymerize it again. So in a way, you could say plastic is sort of a solid version of oil. And if you then make a nice chair out of it and use this chair for 2 generations and then recycle it, I don't see any problem actually in the use of plastic. The problem only comes with behavior of humans. If we throw it in the ocean or in the environment, of course, that's not very nice. But that's not my point. Just remember, there are really, really important catalytic processes that enable our beautiful life. But one key aspect I wanted to bring to your attention is that all of these catalysts that I've shown you that were sort of catalysts of the last century contain metal as the active principle. And this is also reflected in the Nobel Prizes that were given over 100 years, actually from 1909 until 2010, with Suzuki Sensei, of course, from Hokkaido University, being the last one in this series. You see that all of these prizes, there were 17 Nobel Prizes given to chemical catalysis over this century, were given to research on metals as the fundamental catalytic principles. In the early days, Haber and Bosch, of course, I showed you the Haber-Bosch process, and then Ziegler and Natta for the polymerization, that was also metal-based, Knowles, Sharpless, and the great Ryo Noyori from this beautiful country for asymmetric transition metal catalysis, and then Chaumer, Schrock, and Grubbs for, you know, making carbon-carbon bonds with metal catalysts. Ertl was a German guy who understood or provided an explanation of the mechanism of Haber and Bosch. And then recently, Haig, Negishi, and Suzuki for making also carbon-carbon bond cross-coupling using transition metals as the catalytic principle. And this has led to the situation that chemists actually thought over those 100 years, and I was among them, that for catalysis, you always need as the active principle a metal. A metal is required for catalysis. That's what we all believed. And that's also what you found in textbooks. This is one of my favorite textbooks, Classics in Total Synthesis. You know, you can really learn a lot about chemical synthesis from this book. It's very, very comprehensive. You know a lot. You basically read this book, you know organic chemistry a lot. I mean, you know, and you can make a lot of molecules. Everything is in there. But they define asymmetric reactions, asymmetric catalytic reactions, where you make now mirror image-like molecules, like, you know, left hand and right hand. There are molecules that behave like that, and they are different in the human body. And they say that when it comes to making them, you only have 2 options. You can either use an enzyme, like the protein catalyst that mediate photosynthesis, or you use a metal complex. That was sort of the state of the art in the 1990s when I was a graduate student. And that was also sort of my spirit. I thought, you know, that's the rule. But my dream was to develop universal catalysts, because I understood catalysts are very important for our life. And I wanted to develop universal catalysts that can be used for any type of reaction I wanted to catalyze. This is actually, by the way, still what I want to discover. And so I moved to Scripps Research Institute. Professor Hawkin mentioned it. This is a beautiful institute in Southern California. It's actually located on a golf course. My office was up here. This is actually where my boss resided, and my office was next door, and we had an ocean view. And it's on a golf course, and I could see the whales swimming by at winter. It was just remarkable. And of course, we were focused on the science. And the science at the time was catalytic antibodies. And that was something he discovered, Richard Lerner. And he was also the president of this institute at the time, a medical doctor, actually. He was an immunologist and virologist, and became a chemist actually throughout his career. It's really fascinating character. Unfortunately, he passed away in December of 21. So he witnessed this Nobel Prize, but yeah, unfortunately, he couldn't live longer and enjoying it with us. But he had this idea in convincing antibodies to also become catalysts. Antibodies are not made for catalysis, of course, in our body. They're made to defend foreign organisms, bacteria and viruses, and so on. But he convinced them or trained them to become catalytically active. A really fascinating a topic for me at the time. And so I joined him for a couple of years during this period until December of 1998. And my work was sort of focused on using them like a chemist on a large scale. So can you use antibody catalysis on a multi-gram scale? And I wanted to make a compound that is almost a pharmaceutical. This aldol product here, it's called an aldol product because of the hydroxy group and a ketone. And I used an antibody that they had developed before. Actually, this is the reaction I did in a plastic vial. And by the way, plastic, exactly. And it's a mix. You can see here there's a organic layer, toluene, and an aqueous layer in which the antibody resides. And if you would carefully shake this mixture for a couple of days, you could isolate, or 3 days, you could isolate 10 grams of the pure product in perfect enantioselectivity. That means only one hand form was isolated. So that was very exciting. And you can see us during those days celebrating the 10 gram of this material that I made. But there was more than for me to do. And sorry for the non-chemists, we are getting a little bit chemical now. I wanted to understand how this antibody mechanistically operates. How does it catalyze this aldol reaction? And we had a crystal structure, an X-ray structure, actually. So chemists also use X-rays as to get a structure of molecules. And we had a very good resolution of this antibody active site. And what I found was really shocking for me, because there was, first of all, there was no metal. And I was like, wow, how is that possible? I thought catalysts always need metals. But actually, unknown to me, biologists already knew that enzymes actually come certainly with metals, but they also come without metals. I was surprised, right? And what I found was in the active site of this protein was an amino group and an acid. The amino group was provided by the lysine residue. That's one amino acid that has one amino group, an additional amino group actually. And the acid was a tyrosine, another amino acid that had a phenol. It's a hydroxylated benzene that was hydrated also. And I immediately sort of realized what that meant mechanistically. It meant that these carbonyl compounds that I brought to the reaction are converted into iminium ions and enamines. And the enamine is nothing else but sort of a anion equivalent made under physiological conditions in water. Normally, it's a very reactive species, but nature has evolved a nice strategy now to make this possible under these physiological conditions. And this enamine is then a nucleophile. It reacts with another aldehyde, and ultimately you form this carbon-carbon bond, which is key to chemistry, making these carbon-carbon bonds. So I understood the mechanism. It turns out the biologists already knew that kind of mechanism. They called it class 1 aldolase mechanism. That means there's also a class 2 aldolase, and there is actually enzymes that have a zinc ion in the active site, and these are sort of form metalloenolates, zinc enolates in the reaction, showing you already kind of the duality of biological catalysts. You have some with metals and some without. But anyway, so this was my sort of understanding of the mechanism during my postdoctoral time. And then later in 1999, when I became an assistant professor, I asked myself this question, how is it possible that all this protein needs is an amino group and an acid? And can we not also use maybe an amino acid as the catalyst? It's a very simple idea, but that was actually key. And I thought of Hajos Wiechert, proline. Proline is an amino acid. Actually, proline is an amino acid that we can make in our own body. It's a non-essential amino acid. You can eat it, actually. It's made in plants, in all insects, in all animals. And it has an amino group and it has an acid, very much like this protein, which is, of course, a huge molecule, very complex and made in a very complicated way. So can I use a simple amino acid as a catalyst? That was sort of the idea. And it turns out I can, actually. This was my first scientific independent experiment done in June or so of 1999. And what I realized was that proline, arguably a relatively large amount, 30% more, I say more to this in a second, catalyzes this aldol reaction of acetone and an aldehyde to give the desired product, not only in good yield, but also in excellent enantioselectivity, 98:2, via the same intermediates that the enzyme would use, an iminium ion and an enamine. So that was the discovery. And it was super exciting because all of a sudden, at the time, the chemical community was very interested in this kind of reactivity, directly coupling two carbonyl compounds to make these aldol products. It was a big challenge of asymmetric catalysis. And there were 3 labs or so in the world, one in Tokyo, by the way, Shibazaki sensei, one in Stanford, Barry Trost, and me, just I. And it turns out proline, the simplest of all catalytic molecules and an organic molecule, catalyzed this reaction with the highest enantioselectivity. It defined the state of the art in one of the most challenging chemical reactions chemists have worked on at the time. So I was very excited, but I can assure you the scientific community was somewhat skeptical in the early days. And this is actually what always happens when you make a big discovery. There is skepticism, right? Because you're doing something nobody else is doing by definition, right? It has to be that way. And so concerns came, for example, from my colleagues at Scripps. You know, this is kind of a nice discovery, but what's next? I mean, I don't see anything else that can now be discovered. It kind of concludes organocatalysis, probably, was one suggestion. Or I wanted to become an assistant professor in Germany, or somebody asked me to apply. And then they said, yeah, you can work here, but don't work with organic catalysts. I mean, where should this lead you? This is kind of frivolous, you know, forget about it. You have to use a metal as the catalyst, they told me, right? And also, there was skepticism with regard to the catalyst loading, 30 mole%. I have to explain this to you. I said at the beginning, one molecule of the catalyst in principle is enough to make an infinite amount of products, right? But that's kind of an ideal catalyst, and it's only possible theoretically. And in this case here, but still you want to have as little as possible as the catalyst. So, you know, maybe 1% or 0.1% or something like that. But 30 mole% is a huge amount, relatively speaking, because it means basically that, you know, one proline molecule only makes, you know, a little more than 3 product molecules. So that's far away from infinity, right? It's kind of a ridiculous number. I would always argue, but proline is an edible molecule. It's very cheap. You can recycle it if you really want to, because it's water soluble, and there's no problem in using a large amount of proline. It's, you know, it's also environmentally friendly, no problem here, right? But still, like from a scientific perspective, you want to be as low as possible. So there was a lot of criticism in the early days, but you know, over the years that quickly vanished, and we could show this is actually a general principle. We called it enamine catalysis, and we can catalyze many, many different reactions. All of these molecules here have led to a publication and have many more examples, and many useful compounds were actually made. Aldol reactions, also alpha alkylation reactions, transannular aldols, a lot of Mannich type reactions. This is the first example of a catalytic asymmetric direct Mannich reaction of a ketone, an aldehyde, and an amine. Alpha functionalization reactions. So a lot of chemistry became possible. And this was also, those were the early days of organocatalysis. Many groups now started to join the game. Many groups also in this beautiful country, awesome groups all over the world, in Japan, in China, in the US, in Europe, began working on it. And also at this point, industry realized actually the potential. And I wanted to tell this story because it's really interesting. DSM in the Netherlands, they used our proline catalyzed aldol reaction to make this little molecule here. It's an aldehyde, so it's an aldol reaction between 2 different aldehydes. And this compound here, you can convert in 3 simple steps into darunavir. And darunavir, that's very important, is an HIV protease inhibitor. HIV, if you haven't heard about it, the younger generation, this was probably the causing virus of the worst pandemic in the history, in the memorable history of humans. It caused the death of dozens of millions of people on the planet, actually. And there's until today no vaccine to prevent this disease from happening. So all we have are small molecule drugs. And this is one of them, darunavir, and there's 3 others or so. And the patients nowadays live a normal life and die of old age because they take these small molecule drugs designed by medicinal chemists. I mean, I like to say this not to provoke the doctors, and the doctors get a lot of credit from humans because they think they save our life, but chemists also help a little bit in this whole endeavor, right? By designing these molecules and ultimately also by making these molecules. And I'm sort of happy that our process, even though I was not involved in the design of this molecule, nor in the process, our chemical reaction was used actually to make a useful material for humanity. So what we're currently doing in my laboratory, actually I should of course show you some pictures with the call. This was actually on October 6, 21, so roughly 2 years ago. I was just spending a couple of days in Amsterdam with my wife. We attended a great concert. And this is literally when Stockholm called me, now 23 years later after this discovery, they called me and told me, I have good news for you. This is Gordon Hansen. I'm the chairman of the Nobel Committee. I have very good news for you. And I go like, wow, I cannot believe it. Really? I'm so happy. I wanted to thank you for this. And then he said, wait, I didn't even tell you what I'm going to tell you. And I was like, oh shit, maybe they tell me you don't get the Nobel Prize and we will never call you again. Bye. That was kind of a little thought I had, but then they said, no, actually you do get the Nobel Prize. And it was, of course, spectacular. Very, very grateful. This was the day then, because of the pandemic, we couldn't go to Stockholm in that year. So the award came from the Swedish ambassador and given to me in Berlin. And then a year later, actually, we celebrated. This is exactly after the event on 10th of December 22. You see myself here with my auntie, Christiane Nüsslein-Vollert. She's a biologist and the only other scientist in my family. And she also happens to have won a Nobel Prize, actually, in 1995 for medicine or physiology for developmental biology. She's kind of the founder of this field, how the sphere symmetrical egg develops into an unsymmetrical organism. That was sort of her question. Anyway, so I'm in the middle of my career and I have no plans on retiring. She has just retired. I still want to do catalysis. I'm still fascinated with this topic, and I still want to develop general catalysts that solve all our problems and catalyze all kinds of reactions that we dream of, right? And what I have realized in the process is that acids not only dissolve metals. By the way, you can see here gold. This is a picture from a YouTube video where somebody dissolves a gold barrel, like a piece of gold, and puts it into, I think in German it's called King's water, a mixture of nitric acid and HCl that dissolves that and completely, and you get this bright orange solution. But acids can do more than that. They can also catalyze chemical reactions. And in fact, what I have realized is that acids probably are the single most general approach to catalysis there is. And there's a very simple reason for that, and that is because all that acid catalysts need in order to be catalytically competent is electron density in the substrate. And that I know since I was a child. All of the material world contains electrons. Everything, all matter, all molecules, everything contains electrons. And that means that acids in principle can interact with all of these material things, all molecules and matter there is. Maybe not a neutron star, perhaps, but everything else, acids can activate. And this realization has brought us into this field. And what we have realized was, and that goes back to my postdoctoral studies with the antibodies, that the problem of conventional acids that people have introduced, this, by the way, this design came from Japan for catalysis. Akiyama sensei and Terada sensei have used phosphoric acid as catalysts, and they're wonderful catalysts, and they're frequently used, but they have a problem, a little problem, and that is they have an open active site. So this is where the chemical reaction takes place, but there's a big space here, and basically a space that points towards infinity. And the problem with that is that if you have now a small substrate, an unbiased substrate, something like enzymes can handle, and we handle in our own body, then there's a great degree of flexibility in this active site. And this flexibility then hinders your catalyst from being highly selective because of these multiple conformations that the small substrate can engage into. So what we need are enzyme-like confined active sites, I figure. That was kind of my idea. Maybe the second important idea I had in my life. And basically, that led then to the design of catalysts where we take two phosphates and bridge them over an imidonitrogen. And what happens is then, because it's so sterically bulky now, and you bring these two things together, you create a confined, well-defined active site, a volume. And that's why we are calling them confined acids. They're not just bulky acids, they're confined acids because they create, literally, they carve out a chiral space that can be used for catalysis. And you can see this nice, again, in a crystal structure. This is the active site here of this catalyst. We call them IDP catalyst, imidodiphosphates. And this is the crystal structure of TRIP. Also, this specific one was designed in my laboratory and published first. And you can see here, there's an open active site. And here you get this nice confined active site where hopefully now small molecules will be in a well-organized, will behave in a well-organized way, and you can get high selectivity. That was the design. And indeed, we have now a suite of such acids. We call them IDP catalysts when they have two oxygens here. IDP when one oxygen is exchanged to nitrogen, and IDPI when both oxygen atoms are exchanged to nitrogen, a triflulyl imido group. And that has drastic consequences now for the acidity. This is kind of a scale for acidity. The more you go to the right, the stronger the acid. Here, everybody knows sulfuric acid. This is one acid you better don't touch. I know this also from my early days. I had an acid in my sulfuric acid in my jacket, and a little came out, and sooner or later a hole was in my jacket, and the bottle came out because it's so acidic, so aggressive that it dissolved the polymer my jacket was made out. And so this is sort of in the middle now. And if you go to the right from that, you have acids that are even stronger than sulfuric acid. They're very, very strong acids. Actually, they have been called magic acids, these extreme versions here. And we have the strongest chiral acids on the planet, to my knowledge at least. And we use them now as catalysts. And with this universality of acid catalysis, you can imagine how busy we are right now in my group, because pretty much any reaction you can catalyze with acids. And it's just sort of the choices we make that limit our discovery in a certain way. And I'd like to share for the experts, I'm sorry for the non-experts, I will show a little bit of chemistry now, some of the reactions that we have been able to discover. One that's interesting in terms of these early days with proline, another aldol reaction, actually named after Mukayama, a great pioneer and wonderful chemist, unfortunately passed away just a few years ago. The Mukayama aldol reaction, where you use now these nucleophiles here and react them with ketones as electrophiles. And you can see now the kind of catalyst loading that became possible over the years. We only needed 0.0003 mole percent. This is actually, in terms of weight, 0.4 milligram, and that's enough to make 22 grams of the product. And we have in this paper actually one example where we went below 1 part per million. We call it part per billion catalysis, even though it's 900 parts per billion, so 0.9 ppm. And with that kind of amount, you can basically use 1 milligram to make 1 mole, which would be 388 grams. And if you do this on a big scale, that would mean that 1 kilogram of such a catalyst, and we can make a kilogram in my lab if we really have to, 1 kilogram would be enough to make a mega mole, which is 388 tons, kind of the world demand of a blockbuster drug we can make with 1 kilogram of such a catalyst. The catalyst loading now is so low that in principle, the agencies that sort of regulate the drug market, they would allow you to leave the catalyst in the medicine because it's kind of a trace impurity, at least in Europe and in the United States. I don't know, in Japan, maybe you have more strict rules, I would assume. In any case, nobody plans on doing this. I'm just showing you to this to illustrate how low of a catalyst loading we have accomplished now. And the reason I'm so excited about this really goes back to these earliest days when people said, you know, this is not a real catalyst you have discovered, and organocatalysis is not efficient, and only metals can be efficient catalysts. I heard all these stories, but in reality now, organocatalysis defines the state of the art in terms of how low we can go with catalyst loading. One example. The second example, discovered by Nobuya Tsuchi. He's now an associate professor at Hokkaido University, back when he was a graduate student in my lab. And that's the first example in which we activate an olefin, right? Like these Ziegler-Natta type polymerization the Heck reaction, and all these transformation I've discussed before, they used olefins, but they always required a metal to activate the olefin. And we can now do this with a simple ID pi catalyst, these very strong and confined acids that we have made with very high selectivities. The other example I wanted to share with you from just last year is by Hui Zhou. She's becoming a professor in Wuhan now and in China. And she discovered how you can add trimethylsilyl cyanide to a ketone. And that was really a remarkable reaction, not because it was kind of unheard of, because this reaction you can catalyze with anything. You can put an enzyme, there are nitrolases, in almonds, for example, that catalyze this transformation. There are even engineered versions of this. You can use a metal catalyst, a titanium catalyst, very powerful catalysts are known. And you can use organocatalysts, for example, Jacobson's beautiful organocatalyst to catalyze such transformations. But none of these catalysts, even the most sophisticated enzymes, could handle the simplest of all. And that's this small ketone here. It's called 2-butanone. So it was kind of an academic challenge we solved with this paper. But more than that, this compound is an intermediate in the synthesis of 3 marketed pharmaceuticals. I forgot the indications, but they're used drugs. And they are made from the mixture of the 2 enantiomers of this compound, because chemists were unable to make the pure enantiomer. And then that leads to the situation where you have to waste half of the material that you have produced. It's a very wasteful and not very environmentally friendly approach to drug synthesis. And so both a technical and an academic challenge that was solved with this paper. The other reaction I wanted to share with you that you really know where organocatalysis is heading right now is the conversion of nerol to isopipetinol. Both are natural products. Nerol smells like lemon or orange. Very nice, actually. Very nice perfume. Also, it's put into soaps and perfumes. And isopipetinol actually is a precursor of menthol. And interestingly, in nature, menthol is made in plants, but not from this compound, but from its enantiomer, from its mirror image. And then nature, quite wastefully, inverts 2 of these stereocenters to make menthol. Sorry, I'm speaking to the experts here, I know. But it was really a grand challenge to do this transformation, and people have figured this is impossible. It was called an impossible chemical reaction. And there's a very simple reason that all of you understand, and that is the product is more reactive to acids than the starting material, but you need acids to catalyze this reaction. So if you add an acid to this, okay, the reaction might take place, but then immediately the product will decompose into something else. And with our confined acids now, they behave like enzymes, this became possible, and we can now make isopipetinol, the right one, in excellent selectivity. And one step further, we can make menthol. This is, despite a 100-year history of menthol technical syntheses, one even from Takeda in Japan, a very, very important one historically also. This is the shortest synthesis of menthol. And it could really become a process. We're intensely working on it right now. And moreover, isopipetinol can also be a precursor for THC and CBD. Both are actually pharmaceuticals also. I mean, they're also used recreationally in cannabis when you smoke hashish. I think it's illegal in Japan. It's also still illegal in Germany. But you can use them in cancer medicine, and it helps to increase the appetite. And also CBD actually is legal, and it causes kind of a relaxed mood, I heard. And in Japan, for example, you can, I don't know if you can buy it, but the legislation is pretty strict. It should not contain more than 0.1% of THC. And the problem, if you isolate it from the plant, which is of course abundantly available, you always have impurities of THC, and that's illegal then. But if you make it chemically now, we can make selectively both of these isomers, and that could be something. So all these molecules are actually billion-dollar molecules on the market. So let me share with you now towards the end of my talk some of the things for the future we're thinking of in my laboratory right now. And one thing I find really fascinating is this idea with acid catalysis. We can activate anything, like even alkanes. And like cracking, in the cracking reaction, I've shown you this is sort of the biggest scale chemical operation. Remember how to make fuel. I want to crack CC bonds, carbon-carbon bonds in these long chain alkanes. That would be kind of my dream, but not like in the steam cracker where it cracks pretty much any bond unselectively and you get thousands of different products that you then have to separate. I want to develop catalysts that do this selectively, only one bond. Is that possible? And this is something we do now at ICRED, at Hokkaido University. And such a chemistry would actually involve a carbon with 5 bonds. Normally, organic chemists, get shocked when you propose something like this. And if you propose it to your professor in an examination, you're kicked out and you lost the examination. Sorry, you're out. Because somehow organic chemists believe it for a long time, it's impossible. But it's not actually, despite the fact that if you see this on the internet, they call it a Texas carbon, because it has the carbon now here with these 5 bonds. It's actually a known entity. And that's what we organic chemists forget. George Olah has clearly shown these compounds exist, and they are probably the intermediates in catalytic cracking. And so with my team here at ICRED, we're now trying to, this is the team, actually, this is not the most recent picture. We're trying to do this. And very lately, we have been successful. Ravindra Raut and Nobuya Tsuchi have developed what is the first catalytic asymmetric cracking of alkanes. A unique transformation. You don't find anything like that in the literature or in the history of chemistry. You can take alkanes now and selectively protonate one carbon-carbon sigma bond to even get products with high enantioselectivity, like making these mirror image molecules with selectivity. So this is our first big paper coming out of the investigations here at ICRED. Hopefully we'll submit this very soon. I'm working on it literally right now. And so with that, what can chemists contribute to the future? I've mentioned this in the beginning. Catalysis will play an important role also in the next century. And you guys, the young generation, you should think about targets for your own career. I think this one would be a good target, sort of an artificial photosynthesis. Remember this dream reaction, convince CO2 and water to react, but to give oxygen as one product, and then synthesis gas as a byproduct. So that would be an alternative to carbohydrates. And then synthesis gas via Fischer-Tropsch, I've shown you this process, can be converted to fuel. So from this way now, you can make fuel from CO2 from the air. That would be a nice and completely sustainable way to use still combustion engines. If you're very attached to a Toyota car or Lexus car, you could still do it in a green way, actually, if you would be able to develop such a process. And there are people already working on this. It's not very efficient, but it's working. And in principle, this should go. And I have the tendency, I always go to extremes. And my extreme reaction that I really want to work on now would be this one. It's kind of the essence of photosynthesis: convert carbon dioxide from the air, take it out of the atmosphere again, so solve climate change, and react it in the presence of light and catalysts to give carbon and oxygen. Very simple. Splitting of carbon dioxide. I can assure you nobody else right now, to my knowledge, works on this transformation. And I feel like back in the old days with proline, kind of insecure. Is this really a good idea what I'm doing right now? And back then I kept it a secret, actually, that I was working on proline. But now I don't mind. I don't mind telling you this. It's a kind of crazy idea, but it's a possible idea. It's possible. It needs 300 nanometers. And I want to discover this transformation because it would give some more meaning to our name, the Max Planck Institute for Kohlenforschung, because nobody does work with coal anymore, and we would be making now coal from carbon dioxide. So with that, I'd like to thank the people. This was the celebration that we had in Mülheim in the summer of 21, celebrating all the previous co-workers came also from Japan, celebrating the Nobel Prize. I would want to thank them. This is the day of the announcement when we then drank 113 bottles of champagne. The whole institute was dancing. The funding agencies, of course, also ICRED and Hokkaido University for generously funding our work. And I wanted to share a few more pictures with you so you get a sense for my operation here. We're now a very big group. I'm very proud. We're 9 people, as you can see here, very motivated. We want to change the world. Again, it feels like the old days when I started at Scripps with a small team, and then it became bigger, and we're very motivated. And this is the interactions I have. We work with doctors. Tanaka Sensei is shown here, and Maeda Sensei, the head of ICRED. We do combination of AI robotics, high-level computation with experimental work. We do fascinating structural work. I mean, can we make sort of molecular motors that go into one direction? Really, really fascinating corporations that we have here. I'm very, very excited about this. And also, I have lots of fun. It was a great honor visiting Suzuki's statue, going to the onsen with the team. And when they did this little cake for me, this is an edible Ben List, actually. And yeah, last but not least, Maeda Sensei, who has invited me to be part of ICRED and professor at Hokkaido University. Thanks to him. And thank you very much, Professor Hokin, again, for having me here today. And thank you all for your kind attention, also online. Thank you. Thank you.
Thank you very much. Thank you very much, Professor List. When we come to think of this situation, it is amazing because we have a great opportunity to have a lecture directly from a Nobel Prize laureate in person, face to face. It's a pleasure to have such a nice opportunity. So this is a time. This time is open for a comment or question from the audience or the website. Is there any? Do not hesitate. Any question or comment to his to this wonderful lecture? Please. Could I have a mic or something? Like, could you use or speak loudly?
Yeah.
Okay.
But then they will not hear you online,
Okay.
of course.
Thank you very much, Professor, for such a captivating talk.
Thank you.
You started the reaction with the proline as a catalyst. So why proline? Was it special because it is a cyclic amino acid?
Yes, very good observation. It's a cyclic amino acid. It's the pyrrolidine, as this heterocycle is called, is privileged in forming enamines. So it's better than the primary amino acids.
Okay.
The primary amino acids make imines, but they don't go to the enamine. So that was kind of it's a privileged structure. But I have to also admit something, and that was in the late 60s. There was a group in Germany and one group in New Jersey in industry, and they have found proline as a catalyst of a exotic transformation. It was never used really, and they didn't understand at the time what was happening mechanistically. So that came to my mind, and then I took the two things together, right? Realizing, okay, proline actually is an aldolase, and so this is kind of the encouragement, but it was kind of a chemical design.
Okay. And in another work, like confined acids. So in that reaction, what factor decides the enantiomeric excess? Which form should be excess? It is ruled by which factor?
Yeah, it's unfortunately, it's well, it's not unfortunate actually. The way it works is, if you think about it, the hand, right? It's chiral. There's a left hand and a right hand, and they're different. And an object that is also chiral, will be in different forms, in different shapes in this active site, right? And there are multiple interactions that take place. There's sort of hydrogen bonding, ionic interactions. There's dispersion is a very important factor. I don't know if you've heard about it. It's kind of a very subtle physical force, which, especially if you have multiple atoms, plays an important role. Pi-pi interactions, all of these things play a role. And it's like pretty much like an enzyme. And so I cannot, just tell you this is one specific interaction, but it's the confinement that makes it possible. It's the shape of the active site and the pre-organization of the substrates in a certain conformation that is bound to react in a certain enantioselective way.
Can you able to decide which enantiomer will be the excess?
Thanks for this question. Yeah, because yesterday I have just had this team meeting with Maeda Sensei's group, and this is why I'm here. I want to accomplish this. I want to be able to predict, enantioselective catalysts, but the world is not there yet. I mean, we're working on it, and maybe we are really the spearhead in the world. It's a unique program they have at ICRED. But it is also extremely difficult. And that is because the energy difference is just 2 kilocalories per mole to have a significant difference between these two left and right-handed. And the computational error is typically larger than that. So the number we need actually is sort of, within error. That's the problem right now. But as I said, I think it's possible. And with the increasing computer powers, with the sort of advancements of computational methods also and technologies, with machine learning and AI, and with the team doing still experiments, I think we can do this at some point. But we are far away from that, unfortunately, still. Yeah. My pleasure.
Thank you. Any other, please? Mike, please. The other. Yes. Go ahead.
Thank you for your presentation. So at the end of the speech, you explained the light reaction. So we'll utilize the light to the reaction of protein and so on. So if you saw, what kind of light do you use?
For the CO2 splitting?
Yeah.
For the CO2 splitting, it's 95 kilocalories per mole energetically uphill. Like the photosynthesis, it needs light or some other energy source, but ideally light. And 95 kcal per mole is roughly 300 nanometer. So it's a UV light that you would need. So we need that kind of amount, 300 nanometers UV light. Yeah.
Thank you.
Mm-hmm.
Go ahead, gentlemen. I think mic is not on, right?
Yeah, it's not on.
Okay.
Yeah.
Go ahead.
As we know, the carbon have the 4 hands. That means carbon atoms. So here you saw the Texas carbon that has the 5 hands.
Yeah.
So what types of molecule we can predict, or how can we use the 5 types of 5 bonds with carbon?
How can we use it?
Yeah, but how can I get this?
How can I what?
How can I how can we get and use the
So you
carbon with 5 hands?
Yeah, you need actually very strong acids. That's the fundamental principle. And that was already something Ola has described. And he called these acids magic acids. They were really, really strong. I mean, he tried to destroy a candle with these acids. And the candle is made out of pure hydrocarbons, right? And remember what I said about acid catalysis. All that acids need is electron density. And there is electron density in hydrocarbons, also in alkanes, right? In the bond between a carbon and a hydrogen, there's electron density in between. And there's electron density between the carbon atoms. And this is kind of a not very accessible electron density, but with very strong acids, with the proton as a really tiny particle. It's a sort of super small, it's just sort of a nuclei, right? You can activate them if they're strong enough. And then you protonate basically a sigma bond. This is how I describe it. There's complicated models that describe that, but you need a strong acid. And then you have what is called a carbonium ion. Yeah. And a carbonium ion then can engage in multiple reactions, for example, in splitting, in sort of the fragmentation that I've shown you, which is generally called cracking, but it can also engage in other reactions. Dehydrogenation, for example, hydrogen gas can evolve, and then you generate a trivalent carbonium ion, a carbon with 3 atoms around it, and that can also engage in nucleophilic additions. This was all known, but only stoichiometrically and non-asymmetrically. So, and chemists have forgotten about it, right? That's why we came up with the Texas carbon, even though it was kind of known in the textbooks that carbon can have 5 bonds. And what was not known is sort of their use in catalysis. And that's the breakthrough that we have accomplished here now.
That means we can use like the carbon with 4 atoms. So we can use from the next carbon with the 5 atoms in the different compound like this.
No, it's a misunderstanding. It's not like we make carbons with 5 atoms.
Yeah.
we activate a carbon with 4 atoms around,
Yes.
and then transiently get a very reactive carbon with 5 atoms around, and from there you can make other things.
Okay.
But it's never, it's kind of, you can stabilize it and investigate it. Ola has already done this, right? But we are using them as reactive intermediates to do other reactions. Yeah, so it's kind of a reactive intermediate.
Okay.
Yeah.
Thank you very much.
Dr. Murakami, please. Yes.
Thank you very much, Ben. Great
you.
talk.
Thanks.
I have one question about antibody-mediated catalysis.
Yeah.
So, every immunologist, including me, assume that the variable region of antibody can be the catalytic activity. But you suggested that purine amino acid alone can make the reaction.
Yeah.
Is it possible to think that the other antibodies can be catalysts, make your compound
Yes.
in the same way?
Yeah, I mean, that's how I came up with the idea. The antibody catalyzes these reactions, right? So
Yeah,
that was the inspiration.
just purine mediated one.
Sorry?
Not purine mediated one, but not the variable region of antibody.
Yeah.
Is it correct?
I'm not sure if I get your question right, but let me explain to you first antibody catalysis.
Okay.
Antibody catalysis is the idea that we utilize the diversity of the immune system, right? There's, I think, 10 to the 11 or so different antibodies in our body at any given moment. So huge diversity.
Mm-hmm.
And then when I mean, you're an immunologist, so
Yes.
who am I talking to? But it's kind of my primitive chemist understanding. A virus comes into your body, and then that antibody that binds to it is selected and is overexpressed, right? And you get more of that antibody in a very, it's much more complex than T cells and blah, blah, blah. But in a nutshell, kind of that's what's happening, right? Now, if you present the immune system something that resembles a transition state and is foreign to the body, and the immune system recognizes it for the size, then you select antibodies that bind to that transition state analog, and later then, that's the hope, also to the transition state of a chemical reaction, because that's what catalysts do. They bind to a transition state and lower the energy of that transition state. So that was the concept, a beautiful concept based on Linus Pauling's idea that Richard Lerner and Pete Schultz have developed. And there were hundreds of papers on catalytic antibodies. They catalyze many different reactions, but they were never really efficient. The only really efficient one was the one I've shown you, the aldolase antibody. That was really a very good catalyst.
Okay,
Yeah.
Very interesting, because we have a lot of autoreactivity with age, and there are a lot of autoantibodies in our body.
Yes.
So is it possible to make the catalytic reaction, such catalytic reactions can develop the autoimmune diseases?
I mean, it could be. Yeah, it could be.
Okay, very interesting.
It's fascinating.
Yeah,
Yeah.
thank you very much.
Yeah, my pleasure. Thank you.
Gentlemen, please.
Thank you, Professor. I have a simple question. You are explaining about the proline-based catalyst. So, is it cost-effective and more stable than the metal-based catalyst?
This always depends on the reaction, right? But if you think about it, there's a process done on a large scale. And I'm sure this company that is using this, they think about cost effectiveness, and they decided on using proline because proline is cheap. And even if you have to use, 20 more or 30 more %, it's still more, it can in this specific case be more cost effective than using a very expensive transition metal like palladium or something. So it's a case-to-case decision of the chemist involved, whether they use a metal or an organocatalyst or an enzyme. Enzymes are also used now on technical scale.
So how about the stability?
How about what?
Stability.
Stability?
Yes.
That's also, of course, a topic. Proline is relatively robust, and it doesn't really matter because it's so cheap. So after the reaction, they can just put it in the water waste if they want and add more proline and refresh it. But in general, it's a good point. Catalyst stability is important, because you want to use one catalyst molecule an infinite amount of times, right? So one thing that we are doing right now in that direction is to immobilize catalyst on a solid support. And then you have like a tea bag, you dip in your reaction mixture, it does the reaction and you take it out and you dip it in the next reaction mixture. So it can be recycled very easily. So these would be heterogeneous catalysts.
So have you ever used for large scale manufacturing?
Yeah, of course, it's being done. As I mentioned, a drug is made this way, but this is not the only example. There are many examples now.
Okay.
I think otherwise, without that, I'm not sure if Stockholm would have been a possibility.
Okay, thank you very much.
My pleasure.
Any other questions, please?
Okay. I have 3 questions from online on the audience.
Okay, please.
Question number 1. While focusing on biological reactions, you have developed fundamental chemical synthetic reactions. I am amazed at how interdisciplinary your research is. What mindset or approach allows you to conduct such cross-disciplinary research on your own? That's
a good question. I have to first say that interdisciplinarity by itself is nice, but it's not the only virtue in science. It's also completely fine to just study biology or immunology, and you all do this your whole life. You don't have to, work with other disciplines. But it can be beneficial. In my case, it was beneficial. And in my case, it was like during my PhD, and this is also my advice to you PhD student, I learned pretty much anything I could learn about chemical synthesis. This was my topic. I did chemical synthesis in the laboratory, and I learned all of these chemical transformations that are out there. And I felt like, okay, now I'm an expert in chemical synthesis. I need to expand this, and I need to bring in new concepts from other fields. That was kind of my thinking. And I was aware how efficient enzymes are. And so I thought, let's go into biology. And I worked with an MD, and it was a risky move because I left what I knew, right? All the sort of experience I had, and I had to learn something new working with proteins. I never worked with proteins in my life before, right? And that was kind of a risky move. But in my case, it really turned out to be extremely inspiring. And the story was like I've shown you. I worked with the antibodies. We had good success. We published nice papers. And I started to begin to realize for catalysis, you actually don't need metals, for efficient catalysis. It's not necessary. It must be possible also to use small organic molecules, was my conclusion out of that experience. And to be honest, I'm still like this. I like to go into other areas. As I said, I work with doctors. I work with physicists and biologists, and it's always kind of inspiring. I think we can, inspire each other. So it's a good idea. But having said this, first you have to become a real expert in your area. That's very important.
Thank you. It sounds excellent. Yeah. And question number 2. I've heard that machine learning can propose new synthetic pathways. Is it possible for machine learning to discover catalysts with new modalities that can rival metal catalyst, enzyme catalyst, and asymmetrical organic catalyst?
Well, yeah, that's a great vision, and this is the vision we pursue here at ICRAD. There are other institutions in the world that are also doing this, but we are pretty unique in sort of combining machine learning with high-level computation and experimentation, and everybody works together. We have these fusion offices and labs where people really sit in a room together, kind of forcing this interdisciplinarity onto them. So yes, I share that dream. My big inspiration in this was the AlphaFold. It's a Google program, and they basically solved one of the grand challenges of science, and this is how proteins fold. Chemists and biologists didn't know how proteins fold. Then you have a sequence of amino acids, but what kind of three-dimensional shape the protein would take was kind of unpredictable for us. And it was not chemists or biologists that solved the problem, but basically video game programmers, crazy, super smart nerds in London that have, with Google's help, created this program, right? So, and before, of course, chess and Go were solved by these kind of machine learning approaches. And it's penetrating chemistry right now massively, but not yet. It's not yet there where we want it to be, that it can really predict something. I think it can happen. Probably it will happen. Right now, my question is, will it happen in 2 years or maybe in 20 years? I think it will happen, but it's not yet there.
Thank you so much. And then number 3, are there any reactions that only organocatalysts can proceed, whereas conventional metal catalysts cannot?
I think there are a number of reactions where you don't find a metal-based catalyst. However, I would not exclude the possibility that you can, if you wanted to, develop a sophisticated metal catalyst. You don't need to, because these sophisticated metal catalysts are not just metals, but they have a sophisticated organic surrounding, the so-called ligand. And this is often as complicated as the organocatalyst itself. It's like an organic small molecule, right? So the problem will still be there. It's just more expensive and sometimes toxic. So there is no real need for it, I would say. But yes, there are many reactions that we can only catalyze with organic molecules. But there are also, I should say, to be fair, there are some reactions where you really need a metal. The Suzuki coupling, for example, discovered at Hokkaido University, you need a metal. People have claimed I have a metal-free Suzuki reaction, but it never became a reality. There was always traces of palladium that did the catalysis.
Thank you very much.
My pleasure.
I got 2 more questions, but I think okay.
Okay, go ahead.
Okay. The question I've heard is said, what it takes to be creative is freedom. To what extent do you feel this freedom in the research environments of Germany and Japan?
Freedom? Yeah, I love it. Yeah, I love this question. I love to be in Japan. I love freedom. And I really appreciate that you raised this question. And I have to say, there is a tendency right now in many different countries when politics want to influence the research. In a way, it's kind of understandable, right? They give the money. They think they give the money. Of course, in the end, it's the taxpayers that give the money, not the politicians. But they give the money somehow indirectly. And so they want to get something in return. I want some products from you guys. But this is not how fundamental research works, at least. Fundamental research is it needs this kind of freedom and trust. I give you guys are very qualified scientists. I'm sure somehow, with your great minds, you will come up with some, fascinating solutions to academic challenges, maybe. Maybe you get a Nobel Prize at one point. And then perhaps, several decades later, this becomes a product. And this happened all over the place. Basic fundamental research always delivers value for societies, but not in the terms of a democratic elected government. That's the problem, right? So these governments want something in there when they are still in office. They want some products, right? But basic research takes a little bit longer, like 20 or 30 years. So you need this, and it's a kind of very useful thing for sophisticated societies like Japan and Germany to spend money in, and like for a long-term perspective. And these countries are really wise in doing that, and not like other countries focusing on, immediate impact, only do useful stuff, right? And for the long run, I think it's the best. And freedom is unique in the Max Planck Society. So Germany and Japan, we share sort of the freedom we give to our scientists. They can basically research what they want. We give them the money. If it's good science, they can do it, even if we don't know what the outcome will be. But Max Planck is special in that I get this kind of funding guaranteed. I don't even need to apply. So I have a lab of 20 people until the end of my career. And that's kind of nice, because then I don't have to justify what I do. I'm completely free, and it helps me to do crazy things like CO2 splitting. Funding agencies may not fund stuff like that because they have no evidence this is going to work, right? But I want to pursue it anyway. It might take 20 years. I do it. Yeah.
Thank you. This is the final question. Do you have any advice for young scientists and students?
as students, I mean, there is an element of work hard here. I'm sorry, but that's there. But this work hard is sort of just seen from the outside. From the inside, it doesn't feel like work hard because it's driven by enthusiasm. And if you do something enthusiastically, it doesn't feel like hard work when you spend your weekends in the lab doing experiments and repeating stuff. And it's kind of, it looks painful, but it's driven by this enthusiasm for the discovery of something that nobody has seen before. I'm the first to see this, right? And perhaps I can change the world. And catalysis is particularly appealing because often we have this discovery feeling, but also potentially then somebody builds a plant and we save the world. You know, we heal a disease or climate change or mitigate climate change, right? So enthusiasm is the key word here. It's not like the whip and the hard work and the pain that we should go after. We should really follow our enthusiasm. And if you feel this enthusiasm, go for it. If it's there for science, go for it. If somebody tells you there might be a job for you in the future, and then you can support a family and buy a nice house and a car, I would not recommend this approach. I would rather go, if you prefer dancing, then become a dancer, if that's where your enthusiasm is. Because by definition, if you follow your enthusiasm, you live a happy life, right? You do what you love to do. That's by definition enthusiasm. I do what I love. I'm enthusiastic. And then you're happy. Then there's nothing you need. Don't be in this to get a Nobel Prize, because that will be painful if that's your ultimate goal. Love what you do, and then if you're lucky, you get it. If you don't get it, it's also fine because you love what you do anyway, right? It's kind of that's my one key advice. So thank you for that question.
Thank you very much.
Okay, thank you. Time flies, and we are very sorry we have to wrap up this wonderful lecture. Final question: you are working as a PI of the ICLET and the List Research Center. Could you tell me the future plan with the collaboration with the ICLET and your research? I mean, computational chemistry and your conventional chemistry.
Yeah, it's kind of a little bit paradoxical, because in a way, my ultimate plan here at ICRET is to make myself useless in a way, such that we don't need, chemists anymore. We just need, let's say we need a drug, and then you tell the computer, we need a drug against that disease, and then sort of some research is taking place, everything electronically, computation, machine learning. And then this program will come up with a molecule, and then also how it's made. And then it will fuel this information into robots. And the robots will make these molecules. They are catalysts, for example. And then the robots will also use these catalysts in catalyzing chemical reactions. And then will feed back the information they learn back into the machine learning program. So it's basically just somebody sets up and says, I need a solution for this. Probably just saying it like I just say it with words, with the new sort of language-based machine learning algorithms. I think this can be so powerful. As I said, it's not yet there, but it's a great research topic for 20 years or so. And then, basically I can retire and, you can all use robots and machines replacing me, and I can enjoy life, eat good food, drink fine wines, and travel the world. So that's my goal.
Thank you.
Thank you.
Thank you very much. Yeah, this is my second time to enjoy his lecture. Every time when I enjoy his lecture, I can feel his personality and the humanity. I think that the Nobel Prize was given to his personality. Okay, once again, please give him a best applause to his lecture. Thank you.
Arigatou gozaimasu.
Thank you very much. Thank you.